One is that over time, there used to be a running joke that, and there was some truth to it, I guess. There was a running joke that one of the lines was that you had to hire a particular someone to deal with memory management in Cincom Small because it was really complicated. And not only that, but you usually got a benefit out of it. Well, the other side of it was that it was really hard, therefore, for most people to deal with it, which was a problem. This was with the customer's needs and performance and stability and so on. And so we decided to take time and do something about this problem. Now, as you'll see though, if you're a little bit familiar with what's going on, then you can also now apply changes and configure your environment such that it's suited to your application, so you can get significant performance improvements. Now, but usually since there's all this aura of complexity around this matter, we'll take a quick look and see how object memory management works, and then we'll see what has been going on since then. So memory management comes into being because we create objects, and objects have to go somewhere. Now, at first, when you create objects, they have to go in any place, and the first place they go is this hidden memory region over there. So first, you see, great, create objects, awesome. Now, no matter how large hidden is, of course, it fills up. Anybody that knows, anybody that has a hard drive knows that this happens. So eventually, we're going to have to do something with the hidden over there to get rid of the garbage and save whatever it is that it was not garbage somewhere else. And in order to do that, this area, new space, is going to be hidden and two semi-spaces over there on the right. And so what happens is, when hidden fills up, comes a scavenge operation that takes whatever was not garbage in Eden and puts it in one of the semi-spaces, or one of the semi-spaces. And then, Eden starts filling up again, and when it's full, then you take whatever it's not garbage over there, plus whatever was not garbage from one of the semi-spaces, and you throw it into the other semi-space. Whenever Eden fills up again, then you get rid of all that was garbage in Eden in the other semi-space, and it's garbage again, and it's garbage again. But of course, sooner or later, one of those semi-spaces is not going to be big enough to hold all the objects that are not garbage. So what do you do then? Well, there's this area called old space, where objects that survive a number of rounds of this process get tenure. And the thing with old space is that you could look at it as if it was the spillage of new space. So anything that survives a number of scavenge operations goes into old space. And that's great because once objects get old enough, chances are they're not garbage. Most objects die young, and so the approach of new space actually gets rid of most of them. Now, so for new space, we had the generational scavenger that took care of the garbage in new space. Now, for old space, there are two variants of a Mark Suite garbage collector. One is incremental, the other one is stop the world. And they have different advantages, as we'll see. But the incremental, basically, you can run it in steps and you can sweep, garbage in steps and all that. And the stop the world one, that's the whole operation in one go. And in some cases, it's actually preferable. Now, of course, there are some things that will never be garbage. String is not going to be garbage. Chances are, most of the time, the browser is not going to be garbage. Object is not going to be garbage. So why bother trying to garbage collect the class object? So for that stuff, there's a perm save operation that you can perform that promotes old space into perm space. And the beauty of that is that then when you garbage collect, the regular garbage collection, you don't have to wonder whether object is garbage or not. Now, of course, how do you get rid of garbage in perm space then? Well, for that, there's a global garbage collector that collects garbage everywhere, including in perm space. So that's how we clean data. So this is more or less how objects, come into be and where they go and all this. So this is the basic structure we're going to have to deal with the rest of the presentation. So, are there any questions so far? No? Good. Now, right, but how do we do it quickly? So the first thing is, okay, so what is, in this arrangement, what is garbage in new space? Well, the garbage in new space would be any object that we can find from anywhere else. But when we do a scavenge, we're assuming that old and perm are not garbage. So first, we would have to determine which objects in new space are not referenced from any object in old and perm. And the problem with that is that, well, new space is about, a megabyte or two, say, roughly speaking. Most of it is going to be garbage. So most of the time, we only need to find a few objects. And the problem here is that old and perm can be, say, 500 megabytes. So what business is this of having to scan, 500 megabytes just to find a few references to a few objects here and there? So in order to avoid having to scan like crazy, there's what is called a remember table. And the remember table is a list of objects in old or perm that reference an object in new space. So the scavenger can say, oh, those are my roots. Okay, so I'll scan those, then I can find whatever is not garbage in new space by tracing through the remember table and then tracing through any object in new space that I could reach from the remember table, and the rest is garbage. So great, we don't have to scan all that. And something similar happens when we have to do garbage collecting in old space, but we are assuming perm space is now garbage. Why, if the whole point of having perm space was that during ITC you didn't have to scan and wonder whether a string was garbage or not, then why have to scan that in order to determine what was referenced in old space from perm space? And in order to do that, there's its equivalent, the old remember table, the list of perm space objects referencing stuff in old space. And the HGC and the IGC the GC and the IGC use this table to speed stuff up. So this is how we can do these things faster. Any questions? All good? Now this is all very nice, but who decides to run the IGC, right? So let's see. So we have here, right? Now scavenge happens very often. And if the image was responsible to determine when to scavenge or not, you could have the problem that the image would always be late. Because, by the time you realize that you had to do the scavenge, you already ran out of space. And now you have to take emergency measures and start allocating objects in each space. So, and besides, what's going to happen if you find out that you need to scavenge? Well, scavenge. Well, might as well not ask at all, and have the VM do it anyway. Or might. So that's what the VM does. Fills up, scavenge. Now, of course, that means that, well, why can't we always scavenge? Because then we let the image deal with the responsibility of making sure that that can always happen. And why could scavenge fail? Well, because there might not be enough space in old space to hold whatever it is that we're going to attenuate. So we're going to let the image deal with that, because then the image can decide, okay, so there's not enough space. So for instance, the image might say, well, okay, I want a GC, or I'm going to grow, or I'm going to bring up an emergency notifier, or whichever. The image, it decides. And the good thing about that is that then applications can decide what to do. But how does the image know when it has to take action? Because it tells the virtual machine, well, when free memory falls below a certain limit, tell me, so I can do something. And that's why the VM signals a semaphore when object memory starts running low on free space. And that means, therefore, that the image can decide what to do, because now it knows, low space, well, what are we going to do? And therefore, we have this lovely arrangement of responsibilities. The VM does always the same thing, but very few things. Just scavenge and signal a semaphore. And while the image does most of the work, and you can change it. And it's, of course, much easier to change a memory policy class, like we're going to see in a little bit, than having to change the VM by hand and recompile. And of course, you know, even if I thought I was very smart, which I'm not, if I decided to guess, oh, well, you know, applications usually do this, that, and the other, it doesn't matter because I don't know what applications are doing. So it would be bad for me to go and hard code, or me or anyone, right? To go and hard code a particular memory policy administration, you know, a scheme in the original machine where you guys can change it. So that's why we leave it to the image to deal with that. So memory policies. Now, the most important figure that the memory policy has to deal with is what constitutes a memory emergency. So what is load space? Now, since the image has to make sure that scavenge can always happen, then we need to calculate what is the worst possible scavenge that could ever happen. And that's the minimum amount of memory that has always had to be available and free for the VM to produce perhaps a worst case scavenge and still have your application continue running. Because what would happen if there was not enough space? Well, that might mean, for instance, that there was some infinite recursion, that there was something that went uncontrolled in the image. And the VM could at first say, well, I'm going to grow anyway, and let the image deal with it, except that there are some situations in which that is bad. For instance, what happens when you have an infinite recursion in a 64-bit image, and the VM decides to grow all the time? Well, let's say that happens at, you left at 5, right? So at 5:03, you have an infinite recursion. By the time you come in the morning, I'm sorry, but you know your page file is now 3 terabytes, and you know, so your machine is effectively down. So the whole point here is that by letting the image deal with the administration, if for any reason the image fails to administer, sooner or later it's going to run out of memory, and the VM is going to say, you know, okay, I'm stopping you now because you failed to administer. So in order for the VM to not make that decision, the image then has to know what is the worst case scavenge, so it can always prevent the scavenge failure. So first we have that even, and one of the semi-spaces are full, and everything is not get, we're going to assume everything gets tenure, regardless. It doesn't matter that it hardly ever happens. It doesn't matter. It could happen. We've seen it happen, so it could happen. So because we want it to work all the time, not just 99% of the time, we're going to assume the worst case. So that's a part of it. Now, when you tenure things, they may have references to things in use space, right? And that means that if I bring one of those objects in use space to old space, and it still has a reference to object in use space, it needs to go into the remember table. And that means the remember table may have to grow. So I need to account for the fact that the most possible amount of objects in use space, when tenured, may still reference other objects in use space, so the remember table may have to grow a lot. So we have to account for that. Moreover, what happens, for example, when we tenure an object in use space, but, so an object goes from new space to old space, but it was referenced from an object in perm space. Well, that means that when the object moves like that, whatever was in the remember table, so the perm object in the remember table that was referenced in the new space now has to go into the old remember table because now we have an object in perm referencing something in old. So the old remember table may also have to grow. So you see there are all these details going on. Moreover, there's something called large space. We're not going to go into much detail about it today, but basically a lot of byte data goes in there. And when it gets too full, the scavenge may decide, well, it's time to clean it up. And in the worst case scenario, you may have to scavenge the whole thing. So we need to account for that. In addition to this, during a PC, there's this native stack, and there's all these stack frames that are not realized, because they're not actual small object frames. And so we may have to take those, dump them into object memory, so we can empty the stack zone and use it for something else, and while at it, make sure that we collect, and we garbage collect, all the garbage possible during our garbage collect. So that space also accounts for the worst case scavenge. So once we know this figure, a memory policy can tell the VM, okay, if the free memory falls below the sum of, well, either one of the semi-spaces, a reasonable growth for the remember table, a reasonable growth for the other remember table, the stack zone, and the large space, then you tell me, because I need to know. I need to do something about it. So after all this, the picture looks more or less like this. So here we have the strip of memory, that will be the image. And you can see that it starts at 0 over there because that's where we loaded our image. So that's the image size over there, the blue arm. And then, well, the image is supposed to grow for a while until it gets to the growth regime bound, after which the image says, well, the memory policy says, hey, before you grow, I'm going to GC first because I think you're being kind of a hog here. And then we should have the emergency threshold, which is this amount that we've been talking about, the scavenge emergency figure, followed by the worst case scavenge, right? Because we should declare an emergency with a bit of space to have time to react, not when we actually blew the limit. And finally, there's the upper memory bound, which is the amount of memory we said our application will never need to exceed. And that's how we set it up. We just say, for instance, well, our application we know should never use more than, say, 400 megabytes, so we're going to set up an upper memory bound of, say, 600. So if it ever gets to 600 and it runs out of control, it needs to be stopped. Yes?
Is there any thought to, instead of having that be a raw number, something that says never use more than X% of what's available from the OS?
You need to configure that in part because in some platforms it may be difficult or rather convoluted to tell what physical amount of memory do you have on your machine. For example, even if you knew, it may not be actionable because you may have taken a look at the free memory when the machine was not under load, and so you think, oh, I can use 3 gigabytes, and then it gets under normal load, and now there's 1 gigabyte free, but you already saw 3, so there's all this complication. And we think that it's much better for the application developers to say what the upper memory bound is explicitly, because if not, we're forced to guess. We're forced to be smart. Oh well, I know nothing about the post I'm running, but I'm going to pull this number out of a hat and pretend that, yeah, well, you guess you're going to guess wrong. So rather not get into the guessing business and do things right. And moreover, that strip of memory is not a single allocation. So you see there's the growth increments, so all the growth, all the little chunks of memory that the image decided to grow in. So this is the picture. So far so good? Any other questions? No? Awesome. Well, but this is all very nice. It should have looked that way. We'll see. So first, we've been working on this for quite a while, and we found a bunch of stuff. Some of that is kind of simple, and this is what my favorite amusing case. So we have this code that is driving the IGC, right? And so it says, hey, the object memory can tell you which state the IGC is. So we can tell you, hey, so if I'm aborting, I'm going to answer the symbol aborting. And the memory policy has some code that dealt with the IGC and made it move forward. And in particular, when it's aborting, it needs to continue the abort until the abort is done. Of course, because symbols were used, and both symbols spell check, well, that means that whenever the IGC is aborting, the memory policy is going to be for aborted, and so nothing's going to happen. And so the IGC is going to stay aborted forever, and will force your application to do IGC to fix the problem. That's good. So, lesson, if you use code like that, like pass symbols around and then compare them with equality, because etc. No. Now the code simply answers booleans, and so it's much easier to just say, hey, object memory int GC is aborting. Well, if true, then push it along, and then you don't have the problem of the typos. Now, this is kind of amusing, kind of a nuisance. Okay. There are some things, however, that were not so great. This is more like what the picture looked like in 7.7. Now first, we'll notice that the growth region bound is pushed all the way to the left. That's kind of bad because it forces your application to GC a lot. And that bound used to be good a bunch of time ago when applications were smaller, but not today. Applications usually tend to use more than 32 megabytes of memory, so it's nicer not to have started with GC, perhaps like crazy, after 32 megabytes. I mean, your image may be bigger than that. Moreover, there could be cases in which, you see what's happening here, there's an inversion, right? So the emergency threshold is beyond the worst case coverage. So you could get VM failure. The VM decided, out of memory, I'm stopping now. Well, that's not any good, because it causes your application to stop working unexpectedly. So there, that is bad. That shouldn't have happened. And of course, it was easy to have it happen because there's a lot of knobs, and as we'll see. And that's fixed. That doesn't happen anymore. Moreover, what happens when there's a memory emergency? Well, when there's a memory emergency, you say, okay, I'm running out of space. I need to do something, because if not, I have to stop all processes and bring up a notifier that says, you're running out of memory. This is your last chance to debug anything. And it's kind of irritating when you do that, you bring up the notifier, you try to GC, and 300 megabytes of garbage went away. What happened? Why did you call an emergency when there was none? Well, because the incremental garbage collector was being used when there was a memory emergency. What could be wrong with that? That the incremental garbage collector, being incremental, where does it put its mark stack? In memory, in object memory. And what happens? You ran out of space. Why? Because there was a memory emergency. Well, great, awesome. Stop doing that. Use the garbage collector. That doesn't have this problem. It uses another memory area, so it never has to deal with, oh my God, I ran out of space. So stop it. That was too low. Moreover, the growth increments, that's a lot of dots. Because the growth increments were 1 megabyte. Great. What does that mean? Well, first we have the fragmentation problem. We had a customer that reported that they had about 200 megabytes of free memory, but they could not allocate byte array new 600,000. How could it be? But hey, what do you mean you can allocate 600K and you have 200 megabytes free? Well, what happened was every single one of those 1 megabyte segments was at least half full. So, sorry, no contiguous space. Well, so those should have been bigger, and now they are. Moreover, you get into this excessive GC problem, and this just kills performance, because what happens? You get past the growth region bound, and the application is working, right? And it goes, hey, I need more memory, I can't grow anymore. Oh, okay. Well, fine, give me more space. Well, no, because you're too big. Okay, I need to garbage collect. So the application pays, literally, gets out money out of the pocket, execution time, pay. Great. I just GC'd, say, 32 megabytes. Awesome. How much did I get? 1 megabyte. Okay, whatever. So, the application does a little bit more work. Ran out of space again. Okay, give me more space. No, because you're too big. Okay, fine, garbage collect. Pay again. No, I ran out of space again. You can imagine what happens, right? All the poor application trying to grow slowly all the way up to 200 megabytes or a decent size, and it garbage collects like crazy. No, nonsense. And this is just half of the story, because the other half of it is that the memory policy was being so helpful to the operating system, and it was saying, hey, you know what? I just found a teeny tiny bit of memory that I'm not using, so I'm going to give it back to the operating system. So then what happens? Well, the application is working, great. So, no space, I need to grow. Okay, fine, garbage collect. Here, I give you a megabyte. Oh, great, awesome. Oh, look, I just garbage collected a little bit of space. Oh, great, just give it off. I ran out of space again. Okay, fine. Garbage, give me more memory. Well, no, because I have to garbage collect. Okay, fine, garbage collect. Give me a megabyte. Great, awesome, I got a megabyte. Oh, look, I did something. Okay, fine. Oh, look, too much free memory. Give it away. Oh, I need to. It's crazy. It's really crazy. And we'll see an example of what happens, and it's ridiculous. And of course, anyhow. from the past because now we have new tests. This is not the technology that we invented because we can make tests. What can you do with tests and this kind of stuff? Well, for instance, you can write tests that verify that all the 20 some odd instance variables in the memory policy make sense. For instance. And you could actually, in the tests themselves, you could document, okay, this has to be greater than that because if not, you have problems, or this shouldn't be a fraction that is more or less like this and the other because then you're having more problems. And this takes all the guesswork away. No more of this, oh, my brain is big, and I can deal with 25 instance variables at the same time, and all the, complicated assumptions and interrelationships. No, why? Let the computer deal with it. So that's one. So now that also means, hey, we're just shipping a default memory policy, which may not be good for you. Well, then that's fine. Change it, and don't just feel that it's going to work. No. Make sure it works. And now you have the tools to do that. Moreover, let's say that, well, yeah, the values are good, but they could be better. So we also have a suite of tests that will make suggestions. So we'll look at what you're doing, and we'll say, hey, you know what? You seem to have, for instance, quite a few processes running. It would be nice, performance might be better if you increase the size of the native stack so they all fit in there. And again, you don't have to be a genius or do guesswork or anything. It will just tell you. And for the really paranoid, for the people that, like me, for instance, that don't like it when they figure out that they messed up because when you have instance variables, it happens. I don't like it. For instance, I personally don't like to hear, hey, we had these machines and they were being controlled by one of these things and they ran a memory. And when I find out that it's one of these things, I'm not happy. That shouldn't have happened. And so, in order to at least feel better, we also have a stress test designed explicitly to try to crash the image. Its sole purpose tries to blow some assumption away, try to cause VM failure on purpose. And if all of that works, then okay, at least it seems to make sense, and not only that, but we have to actually try to crash it in a reasonable manner, and we couldn't. So that's good. So what happens with all that? Well, first, it can also help us drive decisions about how to do things, and to get information on what to do. Well, Don Roberts and John Brandt have written an earlier version of this tool here. And we took it and we extended it a little bit. And so now you can see, for example, up there, the size of Eden, all the sizes of all the spaces, how many scavengers there have been, how the memory is being used. And you can see here the slopes going up as Eden fills, and then the spike, because you get a scavenge, and then how most of the garbage, new space, most of new space, which is garbage, goes away. The number of garbage collected, the number of global garbage collects, what the IGC is doing and what it has done, and a bunch of other statistics along the lines of, well, how many times the native stack was not big enough, how many times the IGC stack overflowed, etc., etc., etc. And if you want to fabricate situations on purpose that cause problems, no problem. Call the IGC on purpose, call the GC on purpose, call the global garbage GC on purpose, or flash new space on purpose, which is really useful to make old space objects on demand, or run the multi-allocation profiler. Now that button, the multi-allocation profiler, was really useful to me, because while I was making this tool, and improving it and using it, I was noticing that just because I was using the tool, the system was creating a bunch of garbage. So I just ran the multi-allocation profiler on it, and just because the button was there, I found a way to create 3 times less garbage with the tool. And it turned out to be that it was GUI related, and guess what? GUI stuff now can create 3 times less garbage. That's awesome. Less GC work, better performance. And You can, of course, put this tool in graphical mode in your applications because, probably customers don't want to see that. Because the application is about something else. Well, that's fine, because this tool now can also write CSV logs with that log button on there, or you can also load a parcel that loads this tool headless and starts writing a CSV log. So it doesn't matter now. Put it in there, make your application, load the parcel, run the application. You'll have it run, no problem. And then take the CSV log, which will have all the statistics, all of it. And then you can look it in Excel and do whatever you want with it. Find patterns, hey, my uses of memories, like sawtooth or whichever it is. It will tell you what to do. Look, too much GC when doing this type of operations. Well, why? Is it because the memory policy is inducing problems? Is it because my application is creating too much garbage when it's doing a particular set of things? This will tell you. And you can load it headless. So before and after, this is all very nice, right? Look at all the tools we have now. So what happened with this, right? What did actually happen? Well, first, the picture looks better now. There's no more inversion right there. The green arrow is far more to the right, so most applications don't even need to garbage collect for nothing. And the segments also bigger, and so you get even less garbage collection. But of course, this is just a picture. What actually happened? Well, what actually happened is looks more like this. This is some performance numbers from running a set of stress tests. Now, the first thing you'll notice is that in some cases there are 3 bars, so 3 color bars, including the orange one, and in some there are none. Well, that's because the old version didn't even finish. Just did. Which immediately illustrates that the stress tests are actually doing their work. They are, in fact, identifying problems, which, of course, don't happen anymore. Moreover, well, here's something interesting. So if they had worked, the best I could get was getting up to here, and it failed after 1 iteration. Okay, these are 6 iterations, but it failed after 1 iteration. And out of that, I could more or less interpolate that if they actually had finished, they would have taken a day to run in the version without any changes. With some changes, which are the yellow bars, we get better performance, much better, 160 minutes versus a day, and the configuration we ship as a default in 771, well, they're running 73 minutes. And the mix of results, even though you'll see that in some cases the green bars are slightly higher, those represent the rare cases. These other cases in which the green bar is much lower represent the common cases. So of course we optimize for those. 73 minutes versus a day. It makes a huge difference. Now, of course, this is all applications, all object creation stress scenarios. And you may wonder, well, of course, you just fix stuff and you just wrote a test to exercise your fix. That's why it looks good. But my application doesn't do that. Well, of course it doesn't, but I have data. This is a frame from a video from ESA 2009. It's kind of hard to see. Let's see if I can point it with the arrow here. But in here, there's a blurry icon, which is the garbage icon. And what happened was that during the demo of this application, the garbage icon was flickering like crazy. GC. So we took a look at the presentation. Yeah, Martin was there. You remember that. And we approached the people and said, hey, maybe you could tweak a few numbers. And this was before we had any tools. So it was, in a way, kind of an ad hoc change because we had the tools and the code was not cleaned up or anything. But we ended up telling them, hey, change these couple numbers, touch them like this and see what happens. Well, what happened was 2.5 times faster. 2 little numbers. So not even a full set of changes, not even using actually the tool, not even profiling, no, nothing. Just 2 little numbers, 2.5 times faster. So it does make a difference in actual applications. So it's not just, yes, the tests aren't faster because I coded for it. No. Applications are actually faster, and we can show that. So that was for 771. And Since then, we've made a number of changes, and I'm going to go over what has been going on since then. Well, first, I had a slide in Smalltalks 2010, and we said we were going to do all these things back then. This was not done at the time. I gave it up. And we said that we were going to fix or address a few problems with fixed space allocation and improve weak and ephemeral support for some of our lovely partners that are here. And yes, they got it. We were going to make the IGC perform better. We were also going to address the mark stack overflow problem for both the GC and the IGC, so they work faster, so it's harder for them to have a stack overflow. The IGC ran 10-20% faster, the GC 20% faster in very common cases. This thing about the GC moving large space into large objects into large space, there was a GC. We investigated that. We decided against it for now, but that was investigated. And we also provided switches, because what happened before was that there's an array of several numbers that tell the image, well, tell the virtual machine, how large are new space and the semi-space and all these kinds of things. And once the VM starts, they can change. So that's why you have the configuration. Well, the problem is that in order to change the configuration, you have to load the image, change it, save the image, and start it up again. Which makes it hard, for example, to run profiles from a script. Because now you have to load the image, do something, save, etc. So now we have VM switches that override that configuration. So now, hey, don't take our word for what we think is best for a default. And try it. It's easy now. And this is done. Bye. We're done in November 2010. Done. Great. So then I went to Visa. And of course, well, that was then. So I had another slide of things we were going to do. Well, since then we found a way to make the garbage collector up to 40% faster. Of course, it depends on the shape of your image and the relationships between the objects, how many byte objects you have versus pointer objects. But in reasonable images that are not outlandish, I measured up to 40% faster. So we think that is good. The IGC uses less memory because it manages its lists better. Much harder to have it suffer from a mark stack overflow. Moreover, we also changed the IGC driver in the memory policy to be time-based. So you will tell it, hey, do your work, and at most interrupt me for, say, 20 milliseconds. Now, of course, you say 20 milliseconds in your machine, in your development machine, not in the production machine. And even if you say it to somebody in the production machine, so it's actually feasible, that doesn't mean that 20 milliseconds today is good for tomorrow when the machine is under load and the IGC can't do any work. Because 20 milliseconds at one point may mean a lot of work when the machine is doing nothing, or 20 milliseconds may mean little to no work when the machine is under load. So that means that you have problems that way if, say, the quota was just based on go and mark so many objects, or go and mark so many bytes, because we take different time to do that. So what's important here is the time, then just have it deal with time and have it adjust itself. So if it fails, if it can't meet the requirement, adjust and quickly. So you don't have to do this, so you don't have to guess. That's the whole point. No guessing, no guesswork. Because if you guess, you can guess wrong. That's bad. Moreover, the memory policy can also look at the IGC stats that are shown in the memory monitor and figure out cases in which, the image is just working against me. It's doing something such that I will never finish marking, for instance. Because, you know what, the image is 100 megabytes, and so far I have marked 300 megabytes. So I can't win. And when that happens, stop. Stop wasting time. We're not going to win. Stop it. The IGC now can tell that kind of stuff.
So Andrés?
Yes.
That means that if you're doing something like a large read
On the lines of hacking the memory policy, doing overrides, and of course every time that we change the memory policy, you have problems because you have to redo all this stuff. No. Here, we'll give you a switch. If you know you're going to read a whole bunch of stuff from the database and nothing is garbage, stop the IGC completely. not gonna get garbage, why bother? Turn it off. It runs much faster anyhow. And then when you're done, you just turn it back on. It's just, object memory, current memory policy, allow etc colon false. And when you're done, the same thing, allow etc colon true. Done. And we also have a bunch of fixes. We fixed the old remember table, become got rewritten, fixed space got mostly rewritten, etc., etc., etc. Well done. Fine. That is done too. That was done in August 2011. And that was fun. Yes?
What's the impact on become? Was it just performance or something?
It
Yeah, I
did
would know a little bit
not
more about
work.
that.
It did not work 100% correctly in every case. That was the problem. And of course, now we have a test suite that actually verifies that it works in every case, not the common case, and every case. So there's, I don't know, 300 and some tests, I forget, there's several hundred tests just for become now. So that we actually ensure that it does work in every case. And right here, yeah, okay, fine. I admit, you're gonna tell me, oh, come on, you're clever, you can deal with this. Okay, fine. Yeah. But why, why should I, take a credit on my own cleverness when I can have the machine verify? No, here. It works all the time. It doesn't have to come to, me having a little bit of inspiration. The machine can deal with it. Now that was then. So what will VisualWorks have in the future then? Well, we will have a rewritten scavenger. And why did we do this? Because as we did all this work, we found a number of deficiencies that could only be addressed by rewriting the thing. And as a result of this work, we are going to have remember table optimizations, like not bother putting stuff in the remember table that doesn't have to be there. So the scavenger will do this work. We also have for the future, we will have a new 64-bit class table management that is far more effective with far less code. Far less. And we like less code. We like less code. Why? Why do we like deleting 1,000 lines of code? Well, because then we don't have to deal with it anymore. Much less places for bugs to hide. In fact, in the last 5 years, we have delete, not just put away. No. Delete 30% of the source code of the VM. Why? And we've been adding features and new ports and everything while at it. But this type of stuff is really important for us because then when we need to do our due diligence and make sure this actually works, not 99% of the time, not on my machine and just my machine, but actually works, it's very helpful not to have to deal with artifacts either to begin with. We also added, just because we felt like it, over 2,000 new tests. So there. No assertion failures, no errors, no crashes. And of course, if you take that test suite and run it on the older version, then you do find symptoms of problems that are now gone. So it's not just this that I wrote, assert that one print string is, quote, one, quote.
Yes. Comparison tool with VisualWorks 7.7, I'm curious, do those comparisons apply as is to 7.6 or even more so?
This is 7.8, this is the development version of 7.9 as of August of last year to now. And actually, let me show you. And we also had some fixes for the fixed space parents, copy, the memory policy, etc., 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 etc. So we've been busy, and all that was done, finished, January 2012. So that's, a good 4 months of work. That's awesome. Why is it awesome? Why is it awesome? Because it works. That's why, because it works. I personally care it works. It's not enough, to say, haha, I'm clever, look, I was so clever, I wrote something I can't debug. Doesn't matter. Does it work enough? No. And wrong. Fix it. Done. Moreover, because all of this is backwards compatible, guess what? You can use it now. Now. Go get it. And go and get the tools now. Because all that I told about, the desk, and etc., it's on the CD. So it's for everyone to use, not just me. Everyone, you benefit. And I would really like to hear from you. If you run into problems, if you find a CSV log that I should be aware of, or that we should be aware of, rather, if you run into something interesting that you want to share, send us that information. We would really like to see it. Yes?
How far back in the VisualWorks images would we be compatible with?
I
Like 771,
Yeah.
possibly 76.
Yes, I think so. The thing that you would have to do, you have to probably talk to support about that, but the memory policy, you would have to pick up the latest one and put in the older image. But the VM, yeah, that's backwards compatible. So it's great. Not only faster, better, doesn't crash, and you have the tools to improve performance for your application. Not just what I guess the application should be doing. So, this is my end of the presentation. Do you have any questions? Well, you just have a question. Any others? No? Great.